Hi everyone, I hope everyone is doing fine. So in this lecture, I'll be discussing the electronic spectroscopy part of the molecular spectroscopy. That was the last part. I could not make any lectures in the last 1 month due to some other commitments. And also this is a new setup that I'm trying to work out. If there are some delays and there are some errors that I take time to correct, please bear with it. Okay, so electronic spectroscopy. So far we had seen vibration, rotation, their combinations, and Raman. Unlike Raman, these two are concerned with the vibrational energy levels of the energy levels of the molecule, which are inherently present in the molecule. No matter you apply a magnetic field, electric field, no, even in the absence of that, those energy levels are present. Electronic spectroscopy is similar to vibration and rotation in those terms that they have specific electronic energy levels already present. So what we want to see, we want to study the electronic energy levels. Okay, that being said, so we want to see the transition of the electrons in those energy levels. So for an atom, this electronic spectroscopy, when we study for atoms, it is known as atomic spectroscopy. And that means that you have seen, as in case of hydrogen, okay, it has lines like Lyman, Balmer, Paschen, all those things, which you have read in your high school. But in case of molecules, that is what we are going to study in this lecture. So now molecules also have their specific energy levels. Those are different from atomic energy levels because they are, let's say, they are formed by the molecular orbitals that are formed after the linear combination of the individual atomic orbitals of the atoms. So just like we had done for vibration and rotation, we'll start with the simplest molecule possible, which is a diatomic molecule. Now, let's say a molecule is H2. Now, using Born-Oppenheimer approximation, we can separate all the energy levels. The total energy is a summation of electronic, rotation, vibration, and translation. Translation we had already discarded for studying in molecular spectroscopy because of its very small number, very small difference in its energy levels. But so let's say I just remove it. Okay. So now I have electronic rotation, vibration. We are done with rotation and vibration. So now if we only focus on electronic energy levels, then we'll be done with electronic spectroscopy, the study of electronic spectroscopy. Okay. Now, in terms of the energy difference between two consecutive energy levels, electronic is always greater than vibration, which is in turn greater than rotation. This we already know. And this is approximately 10 to the power 3, and this is 10 to the power 6. Now, with respect to electronic energy difference, not with respect to vibration. Vibration with respect to vibration, it is 10 to the power 3 only. Okay. Now, whenever we study any kind of spectroscopy, our main focus is on selection rule, right? And when we had discussed selection rules, we had said that there are two types of specific selection rules. There can be gross selection rule and there can be uh, specific selection rule. So let's start with what is known as the gross selection rule. Now, in comparison to vibration and rotation, rotation needed permanent dipole moment. Vibration needed change in dipole moment, even if there is not a permanent dipole moment. But there are no such rules for electronic spectroscopy. Even if a molecule like H2 or N2, homodiatomic molecules, which are both vibrationally and rotationally inactive, they can be studied using electronic spectroscopy. And even their vibrational and rotational properties can also be studied using electronic spectroscopy. So that is a benefit of electronic spectroscopy. And why is that these molecules are also active in electronic spectroscopy? So what we want to see the electronic transitions. The electronic energy levels will always be present in a molecule, whether it's polar, non-polar, it has a dipole moment, it does not have a dipole moment, whether it's diatomic or only a single atom or whatever. The electronic energy levels are always present, and the transitions among them, transitions between two electronic energy levels can anytime occur. And if that is occurring, you can very well study the electronic spectroscopy. Okay. So since we had seen that the electronic energy levels are really large than rotational energy levels, for a moment we will consider the total energy to be comprised of electronic and vibration only for the time being, for our simplicity. Okay. And the electronic spectra that you get is known as a band. Why is it known as a band? Band means there are multiple peaks. So there are no specific selection rule. That means nothing like in case of vibration it was delta V equals to plus minus 1 for simple harmonic oscillator, or delta J equals to plus minus 1. Nothing like that. Any transition can occur, and between now electronic energy levels comprises of closely spaced vibrational energy levels. So even among those vibration energy levels, any kind of transition can happen. So all are allowed. So for ground electronic state to first excited state, multiple transitions are occurring among the vibrational states. And that is why you see a peak, you see a band for a particular electronic transition. Okay. Now, if I say, let's say the transitions are something like this. Let's say this is one peak, this is another peak, then the peaks are coming closer. Okay, so all of these are for ground state electronic to first excited state electronic, and in between they have different vibration states, so these are those. Now this is because of the why are the lines getting closely spaced as you go to higher frequency. Higher frequency means higher energy, and we know due to anharmonicity that the energy levels come closer as you go up the energy, as you keep on increasing the vibrational quantum number. That is why the energy levels are close, so the energy required for the transition is also lesser than what you would expect from ground state to another ground state, right? Okay. Now one very important principle of electronic spectroscopy is what is known as the Frank-Condon principle. And at some point of time, assuming you are in either in the bachelor's final year or master's final year, you would have obviously studied this principle at some point of time. That important it is. Now, what does Frank-Condon principle say? That an electronic transition takes place so rapidly that the internuclear separation between the atoms do not change during the transition. So that would mean if this is the ground electronic state and this is the first excited electronic state, if the molecule is like this, the molecule remains exactly like this. There is no change in the bond distance. The bond distance remains the same. The electronic transition are so fast. Okay. And what is the physical significance of that? That we'll see when we discuss the transitions in particular. Uh, Now, whenever you see a peak, the peak looks something like this in electronic spectroscopy. And if you take the specific lines, they go like this. Or the peak could be something like this. Why is that not all the lines have same intensity? That is because some transitions have higher probability and some transitions have lower probability. And Frank on the principle somewhat tries to explain that. How does that happen? Now we'll take a look into it. So we can consider the hydrogen molecule in such a way that you have one. Let's say this is your hydrogen molecule. I've fixed this hydrogen, so we can consider it to be like this, just like we had considered for other diatomic molecules while studying vibrational spectroscopy. Now, since we're considering the anharmonic nature of the curve of the molecule, so what we are going to consider is for the energy curve, we will consider the Morse curve. And we had seen this previously. The Morse curve looks something like this. So you have a Morse curve like this, and these are your energy levels. Okay. This is your V equals 0, 1, 2, 3. Will the wave functions on these look like? Thing like this. Now these are the wave. These are not the wave functions, but these are of the functions which give you the probability. This is something that you know from quantum mechanics. Okay. Now, when you consider the classical explanation oscillation or vibration, classically you have is that the atom, in this case, let's say this is our atom A. The atom A will spend most of its time near ends. That means towards here. Why is that? So that is if you consider a pendulum rotating like this. Here the velocity is 0. So that would mean that spending velocity is 0. That would mean that spend maximum amount of time here as compared to anywhere in between. So this follows that should spend maximum amount of time near the ends. But quantum mechanically, if you consider probabilities, now as you go on increasing the vibration energy levels, the presence of the particle to the ends is larger. How do you so? By the area of curve. So since these are larger curves towards the end of the to end of the this cell, they're spending more time towards the end. But for vibration energy levels, they are going to spend more time closer to the center of energy level. Okay. Now is energy this is nuclear separation, and this particular space is known as a equilibrium internuclear distance. Okay. So how can we study electronic transitions which are between two energy levels with transitions in the vibration energy levels? Now, vibrational energy levels are different for two electronic levels. So that would mean that vibration energy levels here are different from the here. So that means we have to consider separate curves for them. And where the Frank quantum principle is going to help us to study the transitions. So let's say I want to see this is my, oh my god, this is my energy axis, this is my internuclear separation axis. Okay, this is one of my Morse curve. This is another Morse curve of higher excited. So ground state levels represented by double prime and excited state one represented by single prime. So this is your single prime, this is your double prime. These are your energy levels. But so the molecule in the ground vibrational state and is at the equilibrium distance. Because if you look at the wave function, this is going to spend, it has a maximum probability. So that means it is present here. So the transition that is going to occur is a transition. The upper curve is you can say shifted. Let me see if I can specifically get this one, but then all the lines. Okay. Okay. Yeah, this should work. Okay, fine. So that it is doing a transition from the ground state of the ground to the ground state of the first excited ground vibration state of the first excited state. That kind of a transition is occurring here. Now this is a vertical transition, and Planck quantum principle tells only vertical transitions are allowed. So what do you have x-axis? You have internuclear separation or distance. So if during an electron transition the internuclear separation that means the distance between the two atoms don't change, this cannot change in during the transition. So that's the vertical transition. And this will be the most probable transition, and that is why this will be most intense peak. Let me name this as A. This will be the most intense peak. Okay. Classically, this would be the case that since the molecule spends most of its time here in this state, and so there will be only one transition. But quantum mechanically says other transitions are also possible, even their probability might be very less. And which has peaks like this. Okay, so this will be the case for this one. For this one, you will have something like this is the more intense one. These are the less intense. Okay. Fine. Now let's look at another such transition in which difference is that the difference in terms of is that try one thing. Okay. This was not what I was expected. Anyways, so what I want to show is you have one energy level like this, and let's say the other energy level is present at a lower vibrational distance, lower internuclear distance. Sorry. So this is internuclear distance here. It's here. So you can clearly see there is decrease in the internuclear distance of the higher of the excited state. So, but according to Frank-Condor principle, vertical transitions are allowed. So here also vertical transitions only are going to take place. If that's true, what you will have, this is your center. From here, the vertical transition is going to happen to, let's say, okay. So this is your 0, 1, 2, 3. So to the third excited state of the higher excited state, third excited vibrational state of the higher of the first electron excited. Okay. Okay. So now quantum mechanics, the probability transitions occurring to here, here, even to higher excited state is also there. So you will not get only one. What you get is something like this, and this is what a band. Okay. Similarly, now, first case was when the both the electronic state came into the distance. The second case was the excited electronic state had lower internuclear distance than the ground state. So the third case that we are consider is the one in which the, just give me a second, in which the excited electronic state has higher internuclear distance. So that would mean this would be a bit on the side. Okay. Now if I have energy levels like this, and here I have the energy levels like this, like cos theta, and from here I want to do a transition to the higher excited state. There will be a vertical transition. Okay, my bad. Drawing lines are related to this. Oh my god. I guess I should do this. Why is it so difficult? Okay, let's say I want to welcome and do the other way. Just this should have been a straight line. I assume you get the idea. So this transition in this case, the R dashed then R double dashed. In this case, dash less than R double dashed. Case R dashed is equal to R double dashed. Okay. Now if this is occurring when such that internuclear distance in the higher excited state larger than in the lower excited state, lower ground state, there is one more thing happen, and which is of interest in order to see the dissociation that could be occurring in molecules during transitions, and that is what we'll see now. So let's say you have the lower electronic state, something like better. And you have the higher state, some this. And you have the energy levels. Similarly, you have the energy levels. Let's say this is the one. And from here you want to see transition. Okay, I want to shift thing to slightly. Yeah, it should work. So this is the transition that I'm seeing. So when this transition occurs, now in this case, this is much greater than this. So when this is occurring, you see the energy where it reaches in the higher excited state is above the dissociation energy. Okay. So the internuclear distance in the higher excited state is much higher. I mean the distance between the two atoms in the higher excited state is high that the molecule is going to break, atoms are going to break, and they are going to stay as independent atoms here having energy. Now this is the amount of energy which is needed to break this molecule. This is dissociation energy. And here is the amount of energy that is to break the molecule in the ground state. And the difference between this and this is known as the extra energy that is there. Or let's say this is the excitation. So whenever I mean, this is the amount of energy that would be needed to want to excite the separated atoms to the higher electron. Okay. Now, since it has approximately exactly the same energy that is needed for breaking the molecule, these have zero kinetic energy. And what does spectra look like? The spectra will have peaks, and after a certain peak, there is continuum or a continuum. Okay, this is the continuum. Continuum. That means the energy continues. Why is that? So whatever transition occurs here is the point where the molecules are kinetic, and any transition occurring above will give the atoms some extra kinetic energy. Kinetic energy is continuous. So that molecule and the atoms are going to show continuous energy change, and it will not be more discrete or quantized. Okay. So now we are coming to where we need to see the dissociation molecules. So let's take this. We are interested in looking at dissociation energy and dissociation products. Okay. So the amount of energy present when a molecule reaches the atom is equals to what? The dissociation, the ground state, and the excitation energy, right? This is for the higher excited state. Expression that you can. Now, second, another case wherein you can say the high state is already continuous. That means the the spectra would look something like this. pull it. So you have this, and for the higher excited state, you have a something like this. And these are your energy levels. So you see the transitions occurring here to here. So let's say this is the point from where you want. This is the transition of your choice, and this is the lowest energy level at continuum. This is extra amount of energy that is. Now, what is this case? This is when this transition is occurring to some higher excitation, which is above the dissociation energy. Okay. In terms of internuclear separation, this is now way greater, much greater than nuclear in the ground electronic. And what is this energy? This is the X graph, and this is ground dissociation. And so now, in this case, the entire spectra will be a continuum. This is what you will get. No before that. So that is why we came this conclusion. Why we can discuss this spectra. There will be no minimum energy of the molecule in higher excited state. What is it? The molecule will be unstable in excited state, and it will readily dissociate. Okay. Now, sometimes it also happen that before the molecule, sometimes it can also happen the molecule does not have energy higher than the dissociation, but still the molecule dissociates. Going to happen, and what is that phenomenon known as? That phenomena is known as dissociation. It is so when the dissociation is occurring, or when the continuum is occurring, the dissociation energy, then it is known as pre-dissociation. Let's take a look at how the spectra is going. So this is what your ground electronic state. This is your first excited electronic state, and there is a overlap of the continuum of some state. This is your internuclear distance. Let's say there is one here. It has A, B, C, D, E, G. Now, whenever the transition is occurring, now this kind of a situation will occur when Morse of two excited states. Okay. Okay. So for A, B, there will be because the molecule does not have that much of energy for to reach the quantum of this other state. But it C, D, and E, there can be a transition to continuum. Okay, D is D is exactly at on the continuum. C and D are not, but they will still have some probability for C and E. When you consider F, G, and higher states, they are again going to have normal spectra, because the probability for them to coincide, to go to this continuum is very, very low. Okay. Now this kind of a transition from normal energy, vibrational energy levels to the continuum of state is known as radiation transition, or let's say negative transition. Okay. Now, faster than rotational transition, but slower than vibration. So that would mean in such cases you will see no rotational spectra, but will be vibrational spectra. Okay. So this was one important aspect of Frank and the electronic transitions happen. Now we are moving to the last discussion, which is and phosphorescence. Some of many of you phosphorus already know what this is. So whenever transition is occurring, any transition to higher excited state, tend to come back to its lowest stable state. That means lower energy state. This is the case of emission spectra. So far we had seen only spectra. Now this is the emission spectra when the molecules emit energy. So the difference are at fluorescence, there is delta S is, so in this case delta S is plus minus 1. This is fast as there is no change in spin multiplicity. This is slow because of the change in spin multiplicity. Lifetime is less. In this case, it is more, obviously, since it is slow. In terms of graph, if you want to see, let's say this is intense and this is your time scale. Let's say the sometime illumination. This is your okay. After we switch off the illumination, phosphorescence decays slowly. This is a phosphorescence, but fluorescence decays rapidly. That's why those compounds are fluorescent are more useful than which are fluorescent. Now let's take a look at the modes for both the cases. Main focus. So let's start with, in case of fluorescence, what is happening is you have this electronic state and the higher excited electronics. You have this one, like let's say so doing the transition from ground state, let's say I want to oh no, not the entire this one. No. Oh, shift only this. Okay. Cannot waste much time and redraw this. Okay, so let's say this thing, this should work. This the transition is occurring, let's say, to here. Should not have been like this. Let's say from okay, it goes to this, and then from here it can come down here. Obviously, this is the most stable state or the molecule in the highest electronic state. From here, it's going to come down to here or maybe even here, wherever is the maximum probability. This is the percent that is occurring, and there is change in spin multiplicity. This is singlet. This is singlet. The spectra would look something like this. This is your spectra, absorption spectra. Now this comes frequency or energy. Okay. Okay. Now, if you label them, this will be 0 comma from 0th excited state to 0 in the ground state. Similarly, this is 304560. And in this case, this is the absorption occurring from 0 or 0 to 1, 0 to 2, 0 to 3, etc. So if you see the zeros, peak of emission and absorption overlap, and this is something which most of the time in fluorescence. Now, what is that you get? You can get information about vibrational energy of ground electronic state from because of the peaks that you get here. Also, fluorescence takes in the solvated excited. So fluorescence takes place in solvated excited. Those excited states should be solvated. That means surrounded by solvent molecules. Okay, take a look at phosphorescence. Now, for phosphorescence, there has to be a change in multiplicity. That would mean that at some place, two multiplicity should say you have this, and then you have okay. These are your energy levels. And these are the energy levels of another state. This is singlet, this is triplet. And what do you mean by singlet and triplet? 2s plus s is 1 equals to singlet, this equals to triplet. Okay. So in fluorescence, singlet, in phosphorescence, triplet. So this there is a vertical transition. Let's say I shift one again. Let's say there is a vertical transition from the lowest excited lowest ground state to let's say this is a transition that is occurring. Okay. Now it is going from singlet to singlet. Now in the higher excited state, it is going to come down. And at some place, you will see the two energies overlap. And that is where kind of transition can occur from singlet to triplet. And this is known as inter-system crossing. Okay. Okay. Now, why does this happen? Due to in orbit coupling of the excited vibrational energy levels. I mean, the energy levels vibrational in the excited state. And this overlap because of spin orbit coupling. And we know because of spin orbit coupling, the selection rules also get relaxed and be a change of spin multiplicity. Okay. And some examples show good phosphorus. Why? Because in liquid state, there are more collisions. Because of these collisions, they lose energy. Okay. I think that's all there was to discuss. Electronic spectroscopy. We'll take a look at the questions that we have. Let me get the questions. Okay. So from net, the that we have very questions from net. I'll also keep on discussing the questions which were previous. So this question is from net December 2012. The question: the relative population in the two states with energy E1 and E2 is given by N1 by equal to 3 by 2 e to the power minus E1 minus E2 by KT. You have to find G by E1. Now the expression is E1 by G2. This. So this is 3 by 2 and you need by Gm, so that would be 2 by 3, which is your option B. There's another question which came in December 2015 and says, the spectroscopy technique by which ground state dissociation energy diatomic molecules can be estimated. Now, any dissociation, you always go to IR. Another question came. Okay, so this was in the next net. Another question, and the question says, the spectroscopic technique that can distinguish between trans to dichloroethylene and this cis and trans. So what? Okay, so what is the difference in both the cases? There will be in the dipole moment. This will have zero dipole moment. This will have some dipole moment. This will have zero dipole moment. So microwave should be the answer. What the next question we have? Nothing in. We'll move on to gate. The gate we have nothing left. No. We'll move to TIFR, and a very good question came in TIFR 2015. And the question says, the electron absorption spectra of two species A and B are given. In a solution, these two species are dissolved and freely. Using a tunable laser, when the solution is excited at mu A, you get a peak around F1. When it is excited by mu 2, F1 and F2. The continuous line to the following figures describes the relative positions of the forces. Now, there is something. Okay, so frequency of if we had seen in this, and you should remember, the frequency of the emission will always be lower than that of the emission, because some amount of energy is always absorbed in internal motions. If we get option number mu F1. So for a molecule which is having both an F can never have like A and B because peaks are very much separate. There has to be some overlap between the peaks of absorption and emission. If you look at C in the C1, since absorption, if you see in the given figure A and B, the B has which is very intense. But in option number D, the absorption A and B has weak absorption. That is not going to happen. The absorption will stay higher. The option number C is the correct one. And both C and D have overlapping regions for emission and absorption. That is why the answer has to be from C and D only. Okay. I think there was one more question. Yeah, June 2017. And the question says, the first electronic absorption band maximum of a polar and relatively aromatic molecule occurs at 300. Okay, my bad. I should move this. 310 nanometers. And its fluorescence maximum in actual solution occurs at 50 nanometers. So there is a shift to higher wavelength. Why is that? So the large change in molecular geometry in the excited state, there is not very large change in the molecular geometry. Increase moment of molecule in the excited state, that's possible because the dipole moment is on the charge separation and the distance in the atoms. So now slight in this can cause a big change in dipole moment. Decrease in probability of molecule in the excited state, you cannot be sure of that. Lowered interaction of the excited state solvent. Now with the polar solvent, the excited state is going to interact more. Okay, because solvent is also polar, and increase internuclear distance, there is going to be a large interaction. So the correct option is option number. So I think that's all the questions that I had that are there to discuss from electronic spectroscopy. Just take a look if there are more questions. Okay, so the questions as of now in front of me. So just any questions, I will be making one more lecture on vibrational spectroscopy. We'll be discussing the polarization of light. I'll discuss all the remaining questions that are spectroscopy. So in case you have any doubts, in case this lecture using writing pad is suitable or is suitable, please comments. I'll likewise change or keep it the same. In case you have any doubts, in case you have any queries any of the topics, please let me know in the comments. Try to clear them up in the comments only.